In the yesterday class, we stopped here. We will continue with this example. This example is important as this example summarize rule 1 until rule 5. Sketch the root locus for the system using rule number 1 until rule number 5. Okay, let's do together so that we can improve understanding. Now, please plot pole and zero on S plane. Plot pole and also zero. How many pole we have?
Four.
4 poles. Zero, how many?
1 0.
1 0. Okay, now plot the pole and the zero. So 1 here, 0, minus 1 pole, minus 2, 1 0 minus 3, and pole minus 4. Pole at 0. Okay, we have 4 poles, 1 0. That is the first step. Rule number 1 say that we will have 4 branches. Rule 1, 4 branches. Because we have 4 poles. Later we will see what branches, how 4 branches look like. Rule number 2 mentioned that it is symmetrical on real axis. So later we will see it will be symmetry. Rule number 3. Okay, now apply rule number 3. Rule number 3 mentioned that root locus appear to the left of odd number. So now I want you to plot the root locus on the real axis. Counting the number from the right. 1, 2, 3, 4, 5. Now on your paper, plot the root locus on the real axis where it happened. Do we have here on region A? We will have root locus or not? Region A.
No, doctor.
No. Why no? Why no root locus in region A? Anyone can answer? Region B, do we have root locus?
Yes.
Yes or no?
Yes, doctor.
Yes.
Why? Please. Why we have root locus at B, no at A?
A is at the right half plane, B is at the left half plane.
No, that is not the answer.
on the left of odd number.
Left of odd number. This one odd number. This is number 1 to the left of odd number. So we have here. Here, no. We have at D, left number 3. Here also no root locus. We have here equal left to number 5. Any question on this? This is rule number 3. Then rule number 4. Rule number 4 say that root locus start from pole. From pole, it start from here. So arrow from here. Arrow normally out from the pole. From pole here. Here. Okay. And we normally write K0. K start 0, K0. K0 here. Remember that root locus showing the pole when K move from 0 to infinity. It will start from 0, from pole, and at 0, like this. We can see this one. It start from 0, it start from pole, and at 0. But there are only 4 poles. There are 4 poles, only 1 0. So there will be 3 infinite 0. At infinity, 0 at infinity. And because it must start from pole, must end at 0. So the total number should be the same for pole and 0. If not, then the others are at infinity. We call infinite 0. Then this is rule number 3. Rule number 3 is about real axis. Rule number 4. Rule 4 is about starting and ending. Then come rule number 5. Rule number 5, as I mentioned yesterday, is available, applicable only if we have infinite 0 or infinite poles. Normally, in most cases, infinite zeros. Okay? So we need to locate the infinite 0. We have 3 formulas for rule number 5. The first one is number of asymptote. Is equal to number of poles. I used this one hash yesterday, number of poles minus number of zeros. That means 4 minus 1 equal to 3. There will be 3 asymptotes. We will see what asymptote look like. Yeah, asymptote. Then we move into another formula. I will erase this. Formula B is what we call a real axis intercept. Please refer to your note yesterday. Normally denoted by sigma is all pole we add together minus all zero, we add all zeros, divide by number of poles minus number of zeros. That is 3. Adding mean we add 0 pole. We add pole 0 plus minus 1 plus minus 2 plus minus 4. Minus 0, 0 minus 3. Divide by 3. So that means minus 2 minus 7 plus 4. Minus 4 over 3. Minus 1.33. Minus 1.33 is here. This is minus 1.33. Okay, I shouldn't use the arrow. Okay, minus 1.33 is here. Okay, next, we will apply another formula, formula C. I need again to remove this, to erase this. It's about the angle. The angle, if you see the formula, is 2k plus 1 multiply with 180 degrees divide by 3. 3 number of pole minus number of zeros. And k is 0, plus minus 1, plus minus 2, and so on. When k 0, theta is 0 pi over 3, 60 degrees. When k equal to 1, theta is 3 over 3 pi, 180 degrees. When k equal to 2, theta is 5 over 3 pi. Okay. You will get 300 degrees. And if you do it again, k equal to 3, k equal to 4, it will be the same at this pointing at the same direction, the same degrees, because this add another circle, 60 plus 360 plus 360. If you use negative, also the same. If you negative 1, you get 180 degree. You negative 2, you get minus 60. You can use positive, you can use negative. You can find as many as you want, but it will go into the same point. Usually, if we have 3 poles, if we have 3 asymptotes, then we need to find 3 angles. What this look like? That means from 1.33 negative 1.33, we have 60 degrees. The angle is from 0 degree here, x-axis. 180 degrees is here, this is 180 degrees, and 300 degrees, this is 300 degrees. Minus 60 degrees, equal to 600 degrees. We call this as asymptotes. we have from equation, the first equation, we have three asymptotes. So it's asymptote number 1, number 2, number 3. Three asymptotes. What is the purpose of asymptote? The asymptote help us to locate where the infinite zeros, the location of the infinite zeros. That means you can see here both we can see a pole at 0 and -1, both going out, because it must start from 0, from pole, it must end to 0. It will go to find 0 according to the asymptote. And here also. Ideally, at infinity, it will reach the asymptote line, the straight line. And this one also will follow 180 degrees. This is the use of asymptote. And in rule 1, we say we have 4 branches. You can see that we have 1 branch here, 1 here, 1 and 1. 4 branches. That means 4 arrows at the end. Any question on this? One 1.33 is not a real axis intercept. Any question?
I have question. For the K, how do we know that we have to use 0, 1, 2? Or is that
K,
just...
yeah, okay. K, as I mentioned, you can use K from 0, 1, 2, 3, 4 up to how many you want. But usually, as I mentioned earlier, usually the number of K that we will be using is according to the number of asymptote. Here we have 3 asymptote. In equation A, we have 3 asymptote. That's why I use here K 0, 1, 2. If you use K equal to 3, you get again 60 degrees, plus 360. If you use K equal to 4, you get 180 degrees, plus 360 degrees. Okay, so any K, how many K you use, not a problem, but you can see it will rotate to the same point. Then once you find that it rotates, it gets at the same point, then you can stop. Okay? You can use
Okay,
negative also,
understood.
the same answer. But as I mentioned, we have 3 asymptotes, then you actually need 3 angles. 3 different angles. As Kelvin asked, the denominator 3 here is from the formula. Formula is actually pole minus zeros. Number of pole minus number of zeros. 4 minus 1. You can see in the, sorry, this one also. Minus pole minus 0. You can see in the formula that I gave yesterday. And also, of course, because equation A, pole minus 0 is equal to number of asymptote. So actually divide by the number of asymptote. Any other question? This one, this is the one that I obtained from MATLAB. You can see here MATLAB somehow does not give arrow, so it must actually give with an arrow. So like this, and it go up. And this is taken from the book, the textbook. It is here minus 1.33. This is the exact drawing. The one that we did is just a sketching. We can use MATLAB to help us to get the exact drawing. But of course, we need to know the basic theory and how to analyze root locus that we obtain through MATLAB. So we have done rule number 1 until rule number 5. We move to another rule. The root locus can further be refined. We can further refine it. This is the basis, 1 to 5. We can further refine by considering rule number 6 and rule number 7. Rule number 6 mentioned about real exist breakaway and break-in point. Breakaway point meaning that here, this is breakaway point. When two poles adjacent to each other, root locus, we say that it starts with pole. We can imagine that it's something like it collide, then it will break away. That point that collide is called breakaway point. We also have break-in point. Break-in point is something like this. Okay. A breakaway point is break-in point is something like this. We will do later. Okay, when we have two zeros adjacent to each other, the one that we go in to start to go into the zero is called break-in point. And another thing, this is rule number 6. Rule number 7 is about crossing at the j omega axis. This is j omega axis. The crossing point here is called is obtained through rule number 7. Okay, here rule 7. This is break-in point, breakaway point, rule number 6. Let's move. Let's do a simple sketching. As for this example, we can do very quickly. Let's do together. We have 3 poles. I will plot pole -2, -4, -6. we have pole, we have root locus to the left of odd number. So now we know that there are three infinite zero. Then we need to find the asymptote. Asymptote is number of pole minus 0. We have 3. 3 minus 0 equal to 3. And real exit intercept, we add all pole. Minus 0, no 0 in this case, divide by number of asymptote. Somehow in this case also 3. It can be 2, can be 4. Later we see another example. Okay, so minus 2, minus 12 divided by 3. 12 and 6, minus 4. Theta 2k plus 1 over pi over 3. Again, you will see theta is 60 degrees, 180 degrees, 300 degrees. If you do many times, you can see that if theta equal to 3, then you get 60. If theta equal to 2, mean 90 degrees. Theta equal to 4, if number of asymptote equal to 4, we divide pi over 4, then we get 45 degrees. So this is the asymptote, starting somehow from 4, 60 degrees, 300 degrees, and also 180 degrees. And this is the one. Okay, here is breakaway point. And here is crossing the omega axis. Crossing the omega axis. Let's move to rule number 6. I already mentioned breakaway and break-in point. How can we get breakaway? How can we calculate breakaway and break-in point? The point can be obtained by using differentiation. We can obtain by taking dk over ds equal to 0. And we solve for dk over ds equal to 0. As we know, k, gs, hs equal to minus 1. We use this, okay, in order to get dk over ds equal to 0. Then we solve for s. Let's do one example in order to find the breakaway point. This is the same as we did just now. Okay. Plot the pole 0, minus 1, minus 3. Because of this, we have root locus here, poles going out, and here. We can calculate for asymptote. Three asymptote, 3 minus 0. The intercept is 0 plus minus 1 plus minus 3 divided by 3. So minus 4 over 3 minus 1.33. And the angle, if you calculate, will be 60, 180 degrees and 300 degrees. So here 1.33. These are the asymptote, minus 1.33. And if we plot, it will be something like this and like this. Now we want to proceed to find the breakaway point. I mentioned that GSHS equal to minus 1. So in this case, H equal to 1. So K, S, S plus 1, S plus 3 equal to minus 1. Or K equal to minus S, S plus 1, S plus 3 minus S cube 4S squared plus 3S. We need to get dk over ds equal to 0. dk over ds equal to 0. That means we have to differentiate k. K, differentiate dk over ds will give 3s squared plus 8s plus 3 minus. We equate to 0. That means we need to solve this equation equal to 0. If you solve, you can use your calculator because this is second order. You will get S equal to minus 0.45. There are two S and minus 2.22. From here, we know that the breakaway point is between 0 and 1. So must be the first one, 0.45. This is the correct breakaway point. Minus here, minus 0.45. Minus 2.22 is not valid. Any question on this? This is the way to calculate the breakaway point.
Doctor, why negative 2.22 not valid? Doctor?
Because breakaway point is between 0 and 1. Breakaway point must be in between 0 and 1. 2.22 here.
Oh, okay, understand.
Okay.
Okay.
Let's move. This is one example. Find breakaway and break-in point. Here we have breakaway, also we have breakaway point. Breakaway mean from 0, you go out. This is breakaway. Here break in, it go in into 0. Break in point. Formula is the same formula. Let's see, for this one, actually KGSHS is K. You can see that we have a 0 at 3 and 5. How I get this? Because you see 3 and 5. 0, 2 zeros. 2 pole at -1, -2. So S plus 1, S plus 2. So giving root locus, you can also find the transfer function, the pole and zeros from root locus. I remember a question last time. They just give the root locus and they ask student to find the pole and zero. So you can directly obtain from this. This is called open loop. Open loop transfer function. Open loop, you can get open loop pole and open loop zero. Open loop poles equal to -1 and -2. Open loop 0 equal to 3 and 5. So we can use the formula KGSHS equal to -1. Therefore, K as -3, 5, S plus 1, plus 2 equal to -1. And K we bring to the right. You can you can take dk over ds. Of course, it will be slightly longer. It's like uv. Okay, u prime v minus uv prime over v squared. Use that formula. If you solve, I solved it already, please do it. If you solve, you get S equal to minus 1.45 and 3.82. There are two S. Okay, here, I mean, dk ds, you equate to 0. Minus 1.45 refer to this. Minus 1.45. The breakaway point. And 3.82 is this. 3.82. So break in and break away point. Please proceed this to find to solve for to get 1.0 minus 1.45 and 3.82. Let's move on. Rule number 7. Rule number 7 deal with finding the j omega crossing. I mentioned we want to find this point. This is left half plane. This is right half plane. When the pole pass through the j omega axis, the imaginary axis, the system become unstable. Remember the blue line, which is the root locus, showing closed loop poles when K changes. So this is closed loop pole, point of closed loop pole. Okay, and at this point it crosses j omega axis into the right half plane. region, which give the system unstable. Rule number 7, this point can be obtained by using Rose-Hawes criteria. Rose-Hawes criterion. Okay, we know that when we have critically stable system, we will have rho of 0. Remember rho of 0? Rho of 0 give a critically stable system. Critically stable. At this point is a critically stable point. Okay? When it passes the line, then it becomes unstable. So this point can be obtained by using Rose-Hawes criteria. Let's do one example. This is related to Rose-Hawes criteria. Find the frequency and gain K for which the root locus cross the imaginary axis. For what range of K the system is stable? Okay. So in order to find the one that crosses imaginary axis, we need to use Rose-Hawes. Rose-Hawes, in order to use Rose-Hawes, we need to find closed loop transfer function. Is G S over 1 plus GS HS. If we have K, then K here. In this case, it's just HS equal to 1. Then K S plus 3, S plus 1, S plus 2, S plus 4. Divide by 1 over K, S plus 3. If you solve, you get K, S plus 3, S to power of 4, 7S3, 14S2, 8 plus KS plus 3K. Then we can use Rose-Hawes. Remember the Rose-Hawes table, RH table. It starts with S to power of 4, then 3. Then we write the coefficient 1, 14, 3K. Here 7, 8 plus K, and 0. Please revise Rose-Hawes. Here you will get 19 minus K. I just write the answer, 20K here, S to power of 1 minus K squared minus 65K plus 720 divided by 20 minus K, and 90 minus K, and S to the power of 0 is 21K. Rose-Hawes, then in order to be critically stable, there must exist rho of 0. Rho of 0 will happen here. Rho of 0. So this one cannot be rho of 0. Okay, because 90, if K0, then 90 minus 0 is 90, not rho of 0. Rho of 0 can only happen as at the line of S to power of 1. When the equation here equal to 0. Okay. we solve. Minus k squared minus 65k minus plus 720 equal to 0. If you solve this, you get k 9.65. That is the gain when rho of 0 happen, when system is critically stable. Remember that in the last course, when you discuss rows of width, row of 0, you have to later go up to the line before it, okay, in order to get the frequency. So 90 minus k s squared plus 21k equal to 0. I take this one. This is the what we call the auxiliary polynomial. Auxiliary polynomial. Please refer to the previous course. When k 9.65, we have when k 9.65, we solve this equation, we get s equal to plus minus j 1.59. Solving this polynomial. So this is the one when the root locus cross the imaginary axis. It can be obtained by solving the Rosowitz criteria. If I can redraw again the root locus, it is like this. We have 0, 1, minus 2, minus 4, 0, 1, minus 2, minus 4, and 1, 0 at minus 3. Here is J 1.59. Here J minus J 1.59. This is what we meant by crosses imaginary axis. And remember, we start K0 here, K infinity here, K0, and K here is equal to 9.65, K0. Remember our initially like this is K, this is GS. K increase from 0 to 9.65, then become unstable. Therefore, for stability, K is between 0 to 9.65. Because we see that when K0 is still stable, K at this breakaway point also stable, it increase toward right half plane. And at this point where it is critically stable, K is 9.65. We obtain from here. So the region for stability is 0 to 9.65. We can use to design the value of K. If we use K more than 9.65, the system will be unstable. That is rule number 7. We have another 2 rules to discuss on, rule number 8 and 9. That we will discuss in the next lecture on the last 2 rules. Any question before we end our lecture today?